The first speaker is Laura Zabala Urrutia of Tekniker with the paper MPC for a single family house with an heat pump and PV installations. So Laura, you can share your screen and start presenting.
Okay, if you can confirm me that you can see my screen.
Yes, I can see your screen.
Okay.
You can even open your camera if you want.
I tried it, but it's not working. I'm not sure why.
Exactly.
Yeah, I will try it again. 1 moment. Yeah.
Okay.
Doesn't allow me. Yeah, I don't know why it's not working. Sorry.
You can stop. Okay.
Okay.
No,
it's okay. Yeah. So I will present the working with Tekniker has been working within the project.
Sorry, Laura, I need to stop you. You should click on configuration and visualization in because you are sharing the other screen of your computer.
Okay.
So you in the PowerPoint?
Sorry. Yeah.
Okay, or you can decide in this way.
Yeah. Okay, so I will set this down. Yeah, now do you see the presentation? Okay, perfect. Yeah. So hello everyone, I'm Laura from Tekniker and I will present the working with. We have been working within the React project that consists on developing an EPC for a single family house within a heat pump and a PV installation. First of all, I would like to briefly introduce you the React project. This is a project funded by the European Union within the Horizon 2020 program, and it has a duration of 4 years. It started in 2019, and it's focused on geographical areas. The main objective of this project is to achieve the island energy independency through the maximal exploitation of the renewable energy sources, the utilization of these sources together with some storage assets via demand response platforms, and also trying to engage the end user as key players in the local energy community. Here you can see the 24 members that take part in the consortium of the project, coming from 11 different countries. How does the React project try to achieve the goal of obtaining an energy sustainable island community? It proposes two different approaches for the energy management. One of them is based on automatic control algorithms that are aimed at major consumers, such as, for example, the heat pumps or the air conditioning systems. And these algorithms are aimed at managing the different renewable energy sources together with different storage assets. And the other approach that is proposed within the React project is more focused on the user engagement. And for example, it consists on the development of different mobile apps to send some tips to the users and try to, for example, reduce the peak energy through turning on or off the different smaller appliances that can be found in the houses. From these two approaches, Tekniker has been working in the development of an automatic control algorithm that consists on an MPC, and this MPC is going to be tested on a real installation that I will present you right now. The test site is the single family house that is located in the north of Spain. It has a twin installation to the ones that can be found in the island of La Graciosa in the Canary Islands in Spain. This single family house has as HVAC equipment a compact modular equipment that manages the ventilation, heating, cooling, and hot water from the house. This equipment comes with a heat recovery heat exchanger, a reversible heat pump that is used both for heating and cooling, and also with a domestic hot water tank with an accumulation capacity of 180 liters. Moreover, this house also comes with a big installation of 6 PV panels with a polycrystalline technology and with a peak power of 2 kilowatts each one. and also 4 ATM batteries that have a total capacity of 8 kilowatt hours. This installation also has the required technology such as an inverter or some electronics for the logics in order to manage the PV production and use it for the consumption in the house, or also it can be provided to the grid. So this is the general installation in the house that will be used as a test site for our development. And now I will present you a bit more in detail what our development consists on. In order to have a general idea, we are developing an MPC that it will work with predictions on the weather forecast, the energy tariffs and how they will evolve during the time, and also, for example, with predictions on with the PV installation. And the MPC will see how the thermal and the electric demand of the house can be covered in an optimal way by taking into account all these predictions, and it will calculate some optimal set points that will be sent to the different equipment of the installation. In order to understand a bit better what an MPC consists on, I will compare it with the traditional controllers with which we are more familiar. A conventional controller, such as a PID, corrects the current error of the system that wants to control. For example, we think in the case of one car, and we suppose that this PID controller wants to control the trajectory of the car, it will try to correct the current position of the car in order to follow one trajectory. In contrast to this, the MPC has the capacity of predicting what the response of the system will be, and it minimizes the future error. For example, in this case, the MPC of the car could have the capacity of foreseeing what is the trajectory that the car should follow, and depending on that, manage the car. This MPC has been applied in different fields, but in the last years it has turned out to be really powerful for the building's control, because it can use a model of the building in order to predict how the interconditions in the building will evolve, and it can manage the HVAC equipment in order to control these interconditions. Here you can see a more detailed scheme of the structure of an MPC. This MPC has a system model that is used to predict the behavior and performance of the system, and at the same time it solves one optimization problem that counts with a cost function that is used to define the different objectives of the MPC. Also, this optimization problem can include as many restrictions as desired, and these restrictions can be used to define some operation constraints that can be found on the system, and also to fix some upper and lower limits of the variables that are managed by the MPC. The MPC would calculate what is the optimal actuation that should be followed in our system for a prediction horizon. This prediction horizon is typically of 24 hours in the case of buildings, that it will use predictions for the next 24 hours, and even if it calculates the actuation in the next 24 hours, usually just the actuation of the first time instant is applied to the system, and once this actuation is applied, it can the MPC can receive real estate measurements from the building in order to correct and update the current status, and perform the calculation again. So, as I mentioned, the MPC can have different objectives. In this case, our MPC has two main objectives. One of them is to assure the thermal comfort design inside the house, and for that, we define that it should follow the standards that are described on the ISO 7730, and the thermal comfort is defined as a function of both the indoor temperature and also the indoor relative humidity, as both of them can have a great impact on the thermal comfort. And at the same time, we also define as an objective to minimize the electric consumption cost. For that, the MPC will have into account variable energy tariffs, and also the PV production will be boosted in order to self-consume all the production that is possible. As I mentioned, the NPC will work with different predictions. In this case, the weather prediction and energy tariff predictions that are required will be obtained from external services. And for the case of the predictions on how much production will be obtained with a PV installation, what is going to be the electric demand of the house, or the domestic hot water demand of the house, for all these type of predictions, some machine learning models have been developed within the REACT project. These machine learning models are trained with real data taken from the installation, and they also depend in some cases from other variables, such as, for example, in the case of the PV production, the predictions on the weather variables will be taken into account. Another important aspect of the NPC is the model of the system that is integrated within it, as this model needs to predict on a suitable way how the system is going to behave. In this case, we have integrated the following models. In order to model the modular equipment that is used for the HVAC, we have used a physical model that includes all the energy and mass balances of the heat pump and the heat exchanger, and also we have integrated the performance curves that are provided by the manufacturer and that give an idea of what the performance of the equipment will be depending on the operation conditions. For example, what is going to be the coefficient of performance of the heat pump depending on the outdoor temperature that is supplied or on the ventilation flow rate that, with which it will work. In the case of the domestic hot water tank, we have used the stratified tank model that can be found on the Modelica Buildings library, developed by the Berkeley lab. And in the case of the building, we are using a simplified equivalent model to the house consisting on one resistance and one capacitance that resemble the behavior of the building. And in order to calibrate these values of the resistance and capacitance, we are using information from the beam of the house. Here you can see a more detailed scheme of the NPC where all the predictions that the NPC uses are represented. Also, the real states that are read by the NPC, for example, the real indoor temperature or the real relative humidity that can be found inside the building, or the lower and upper temperatures from the domestic hot water tank, and also the actuation variables, that the main ones in this case is the set points that are sent to the heat pump, the storage temperature set point that is sent to the domestic hot water tank, the temperature set point that is fixed inside the house, and also the actuations sent to the batteries. This NPC is an algorithm that has been developed in MATLAB and then translated into Java libraries. And for the integration of it, we have used the React Cloud. The React Cloud is a platform that has been developed within the project, and in this platform, we have all different services integrated, such as, for example, the production services. So the NPC can receive all this information from this platform. And also, this platform communicates with the installation so that all the real measurements can be read and the actuation variables can be set. And finally, in order to have a general idea of what is the undergoing work at the moment and the future steps,
1 minute left.
Yeah, okay. At the moment, we are collecting real operation data from the installation, as you can see here, in order to generate a baseline scenario that can be used to estimate the savings that then will be achieved with the NPC, and also to collect historical data to train the machine learning models, such as, for example, the PV production or the electric consumption. We are working also on the development of the NPC. Especially, we are trying to improve the RC equivalent model that is used for the building, and we are doing some virtual testing for the NPC towards a more detailed model of the system that has been developed in Modelica. And once this virtual testing of the NPC is finished, we will start with the experimental validation of the NPC. So in this future phase, we will let the NPC control the equipment of the house, and we will try to validate that the control operation is reached, so the thermal condition, the thermal comfort is guaranteed inside the house, and also we will try to estimate what are the energy and cost savings that can be obtained with this MPC compared to the baseline scenario that we are going to define with the historical data. That's it. Now, if you have any questions.
Hi, thanks a lot for your presentation, for your very interesting presentation. I have a very quick question because we have few time. Regarding the RC network, did you start it from a libraries or you built it from scratch?
Sorry, regarding the...
Sorry, regarding the RC network, did you...
Yeah.
Okay.
In this case, we have started working with the iSleep library from Modelica.
Okay.
We also want to explore different libraries in order to compare the model we are using with other ones.
Okay, that's fine. Thanks a lot for your presentation.
You're welcome.
Let's do the second speaker. So the second speaker is Barbara Koch or Zeina and Najjar from the University of Freiburg with the paper Assessing and Mapping the Technical Generation Potential from Renewable Energy Sources in the three-dimensional Upper Rhine Region. So you can share your presentation.
Hello, good morning, good afternoon, everyone. Sorry. Can you hear me?
Yeah, it's okay, Ines.
Okay,
yes,
great.
Yes.
Okay, good afternoon. I will be speaking on behalf of Barbara Koch today. So my name is Ines Gavilutz from the University of Freiburg in Germany. I'm the coordinator of the RESTMO project. It is a project co-funded by the EU Upper Rhine, Interreg Upper Rhine program, and it is led by Professor Barbara Koch. So before I hand over to my colleague, Zeina Najjar, I will briefly introduce you to the project. We are a consortium with partners from France, Germany, and Switzerland. We are in our third project year now, and we are aiming to produce results that are representative for other border regions. So just brief information, the project was developed in the framework of the Upper Rhine Cluster for Sustainability Research, which is a research and innovation network linking the Upper Rhine universities. To give you some background information on the region and our rationale, our project rationale, we are focusing on the Upper Rhine region. This includes 3 countries. You can see it here on the slide, and our main rationale lies in the EU Clean Energy for All Europeans package, which actually recognizes the potentials of regional approaches to drive energy transformation and promote also security of supply. Our main goal is to accelerate the transition by investigating synergies from complementary generation, demand, and storage in the region. So our work includes several work packages. One of them is the analysis and mapping of the generation potentials from renewable energy sources in the region, which will be presented by my colleague Zeina Najjar today. This is actually one key input to the modeling. VP3 is the modeling of the regional energy system using 2 energy models. On the one hand, the Regional Energy Planning Model, REPM, which is a regionally focused model that has higher spatial and temporal resolution, and looking at specific concrete technology choices, but not doing any optimization. And on the other hand, we are using, our colleagues are using a model called Perseus EU, which links the region to the broader EU electricity network, and also proposes optimum solutions for most cost-efficient pathways, scenarios to reach EU policy goals. Another work is the social-cultural framework, an analysis of the social-cultural framework, including acceptance questions. It will be presented today by our colleague Philippe Hamman, as well as an analysis of the regulatory and economic framework for a renewables-based regional energy system. And finally, there's a work package focusing on cybersecurity and proposing solutions for cybersecurity and smart grids. This work was actually presented in Rome by our colleague Bushra Kanan yesterday. Without further ado, I will hand over to my colleague Zeina. Thank you.
Yes, hello, good afternoon. Okay, just a second. So my name is Zeina Najjar, and I am a researcher at the University of Freiburg. Just a second. And today I will be presenting to you the technical part of the RESTIAMO project, which my colleague Ines has just presented. So to start off my presentation, I will just define a few concepts like the Upper Rhine region, our study area, and the potentials. And then I will move on to the methodology that we use to calculate the potentials of the two renewable energy sources, wind and solar. And finally, I will conclude. So the Upper Rhine region covers an area of around 21,000 kilometers square and is home to around 6 million inhabitants. It is composed of 3 countries, France, Germany, and Switzerland. In France, we have the whole of the Alsace region, including the upper, the Haut-Rhin and the Bas-Rhin departments. And in Germany, a large part of Baden-Württemberg and also Rhineland-Palatinate. And in Switzerland, it is the northwestern part, including 5 cantons. Our region also includes more than 1,700 municipalities. A very important part of our project has to do with potentials. Now, what do we mean by potentials? Potentials can be seen as a hierarchy, a pyramid, as you can see on the screen.
Sorry if I interrupt you, but your presentation is stuck on the first slide. I don't know if you need
to... sorry. I don't know why.
Because we see the, let's say, the software and not the presenter mode. But
is this better?
Okay also in this way, but okay, it's fine. Yes, now I see
Can you see it?
Slide.
I'm sorry. Okay. All right, sorry. Okay, so this is our study region. I don't know if you saw it before. And it includes, these are the municipalities. And now do you see the slide?
We are seeing the slide. What are the different types of potentials? Okay, so.
Yes, perfect. So the potential hierarchy pyramid, as we said before, the potentials are presented in a form of a hierarchy, in a pyramid form. And as you can see in the pyramid, the largest potential is on the bottom and the smallest potential is on the top. And as we move from one potential to another, it decreases. So we will start with the theoretical potential, which is the largest potential. And it is the amount of energy that is theoretically supplied by wind or sun in a specific region at a certain time. In order to calculate this potential, data about the atmospheric conditions like wind speed and solar radiation and their temporal and spatial resolution are of great importance. After that, we have the geographic potential, which describes the usable area for the generation of renewable energy. And it takes into account competing land uses like urban agglomerations or nature protection areas, and legal restrictions depending on the regional law. The biggest challenge that we have faced so far in the project is the calculation of the geographic potential, because we are dealing with the trinational area. Moving on, we have the technical potential, which is the last part, or the last potential calculated by our project, and it takes into account the technical constraints limiting the theoretical energy yield, like conversion efficiencies of PV modules and wind turbines. And even though we stop at this point in our project, we will also talk about the economic potential, which is basically the economically feasible technical potential in a very specific region in a very specific time range. And the last stage of the hierarchy is the feasible potential, which takes into account the social and organizational dimension, like society's acceptance of wind turbines. Now we're going to talk a bit about our methodology, or the method that we use to calculate the potential for wind energy. So in order to calculate the theoretical potential for wind, which is depicted by the available kinetic energy contained in the atmosphere over an area and assessed by calculating the WPD, the wind power density, which is a parameter. Basically, we need to calculate the wind speed in our study area. And in order to do this, we use data from weather stations. And we homogenize this data using a certain method called the wind speed wind shear model. And then after we find the median wind speed values, we extrapolate them to the different hub heights of the wind turbines, and we calculate the WPD. But I'm not going to bore you with a lot of technical details. After that, we have the geographic potential, which is basically calculating the usable area. The geographic potential takes into account geographic restrictions like orography and competing land uses, like cities and protected areas that are protected by legislation.
Sorry,
and
again,
are removed
I think
from the
you are
study
still
area.
stuck on the 7th slide. So if you prefer, I can share your presentation and you can say next slide. No, it's
sorry,
okay.
that would be perfect.
So you have just 5 minutes left. Can you see my presentation? Check your presentation.
No, perfect.
Okay.
No, it's the slide
Okay.
before. No, even before.
Not before this.
No, before this.
Yeah.
Okay.
Yeah, okay, that's perfect. So in the technical potential of wind energy factors in the wind turbine efficiency for the conversion of the wind energy into electrical energy. So basically you can see the wind potential on the map, and the usable area is the colored areas, and the white areas are the restricted areas, and the technical potential is therefore depicted. Next slide, please. And when we talk about solar PV, next slide, please. So the theoretical potential of solar PV is calculated by calculating the average yearly global irradiation received in the Upper Rhine region by using the software PV maps. Next slide, please. What is interesting about solar PV is at the point of the geographic potential, because we have divided, even though the technology is the same, in the solar PV, the big umbrella of solar PV, into 3 different types of potential: agro PV, ground-mounted PV, and rooftop PV. And they all depend on the usable area. So basically, agro PV and ground-mounted PV are basically the same concept, but agro PV is a new kind of idea that entails tweaking the ground-mounted PV installations on agricultural lands in order to accommodate for agricultural activities. And therefore, this allows for dual land usage, while ground-mounted PV is the normal PV that we know on that is free range. And then finally, rooftop PV has to do is the PV that is found on rooftops. Next slide, please. Next slide, please. Yeah. So the geographic potential, the usable area of rooftop PV can be seen on the figure in red, while agro PV is in green and GMPV is found in blue. In order to calculate the usable area for rooftop PV, it is enough to look at the rooftop area in the Upper Rhine region, while the restricted area for agro PV and GMPV is basically found in the same way by excluding cities, water bodies, and protected areas. And at the level of the usable area, we differentiate between land where agricultural activities take place for agro PV and pastures for GMPV. Next slide, please.
So you have just 1 minute left.
Yes, I can finish in 1 minute. I just need the next slide. Okay, so basically the final step is calculating the technical potential of solar PV, which is calculated by factoring in technical parameters like average module efficiency and performance ratio. And in this figure, the rooftop potential is depicted per municipality to show you another way of depicting results, and also which municipalities in the Upper Rhine region have the highest potential of rooftop PV. Last slide, please. Finally, our the one before. Okay, so the total electricity demand of the Upper Rhine region was estimated to be in 2018 41 terawatt hours, and our preliminary results show that the technical potential in the Upper Rhine region is more than enough to cover the electricity demand. Now, it is important to mention that we also have to account for the heating demand, and remembering our potential hierarchy pyramid, we still have to account for the economic and the feasible potential that are taken on a more case-to-case basis. That's it. Final slide. Thank you for listening. Sorry for the inconvenience also.
Okay, so let me see if there are some questions in the Q&A. Okay, I have a very quick question. Did you consider just PV panel and wind energy, or you consider also, for instance, other sources of energy such as geothermal or
yes, there are other parts of our project, and actually we have looked at all of the potentials. However, the main focus of our research was on wind and solar PV, because we have because they are considered the pillar of future energy. The future energy system. However, we have also looked at biomass, and there was an existing project that ended a bit before our project that was in the same study area. And geothermal energy, a colleague of ours is also looking at the geothermal potential. And we have also looked at the hydro potential, but mostly in the Upper Rhine region, hydro is somehow exhausted. So because of the Rhine, because the Rhine is actually, or at least large hydro installations, that potential is exhausted.
Okay, thanks a million for your very interesting presentation.
Thank you.
I will pass to the next speaker, that is Philippe Hamman from the University of Strasbourg, with the paper Citizen Energy Cooperative in the Upper Rhine region, common issues in the transition toward a decarbonised and decentralized future. So I will pass the floor to you.
Thanks a lot. I hope you can see my presentation, even if it's not in full screen, but can you see it? Yes?
Yes, we can.
Okay. So as Ines mentioned, I will speak about the REST-QMU project as well, indeed, but more from a sociological point of view. Regarding the analysis of a cultural framework in particular, and the integration of stakeholder perspectives. The empirical design of the study conducted in the Upper Rhine region was about 100 interviews with regional key players and with members of citizen energy cooperatives, as well as fieldwork observations. Only to mention some previous publications regarding sustainability research in the Upper Rhine, if you are interested, especially published by Routledge. Dealing with territorial commons and citizen cooperative, I think a first important point is to be clear regarding the definition of the notion, because the term commons, when we speak about energy commons, can draw more or less attention to three dimensions: available resources, the distribution of rights, and or the belief in collective action. So far, citizen energy cooperatives are often presented as the embodiment of common and as providing an alternative model based on the use of renewable energy sources. And more precisely, we can distinguish three main levels of interpretation, in fact: common goods as a system of resources, common project as a goal the member deem it legitimate to pursue, and common action as collective action within a democratic context. So far, relation to the notion of community appear as a central element. I mean, energy commons are not limited to the management of a resource, but it deals with making energy circuits visible. Users may fail to grasp their materiality when they are used to considering only the end of the pipe, the sockets, indeed. So when we speak about energy cooperative, there are two main issues at stake. The first one deals with property. Property does not disappear when we speak about commons, because the different dimension to the reality of property. First, any community must define the rule of access to specific resources and use patterns, so that the statutes of local energy cooperatives often mention their field of action or a local dimension. For instance, you can see on this map an example in Alsace, a very local cooperative indeed around the town of Saverne. Second, property translates into bundles of rights if we consider the works of Ostrom. It means that members are entitled to access and use of the resource, but it is a specific mode of governance as well. The right to vote at the General Assemblies, for instance, is not tied to the amount of shares held, nor is decision making. Third, the shareholders have quite diverse profiles. Of course, there are engineers, teachers, people endowed with technical, administrative, economic, or educational capital, but not only. There are also less qualified people in those energy cooperatives. So that we can consider there are different motives for joining. First, it can be an extension of a professional activity for local energy transition officers or solar installers, or a financial investment, and or a desire to act in a concrete way in reaction against the radical or intellectual postures of some environmental activists. Besides, common action depends on the national and regional legal and socio-economic context. For instance, the legislation is more favorable to prosumers in Germany than in France. And globally speaking, energy cooperatives depend more or less from the local authorities, from a financial point of view, as well as a material one, because, for instance, access to buildings for photovoltaics and so on depends to the possibility that may or not local authorities. A second main issue deals with the point is or are energy local communities alternative to the market or not. Of course, local economic development is an important aim, reinterpreted in terms of sustainability. But there is no unified definition as to what is regarded as an alternative when we speak about energy cooperatives. It depends on the type of energy, fossil or renewables, centralized or decentralized systems, and so on, as well as the hybrid functioning of the cooperative itself, selling often the energy into the common grid. So another important point deals with social sustainability, because different approaches to the question of profitability are at stake. Most often, people say when they are interviewed, they have societal aims and indifference to profit. Okay, but at the same time, this can be qualified in three main ways. First, energy cooperatives do take economic viability into account, especially regarding the feed-in tariffs. Second, the relation to profitability can be different depending on the national context. For instance, in the German part of the Upper Rhine region, we saw that members consider that more as a financial investment indeed. Third, there is a dividing line between project leaders and grassroots members in energy cooperatives, so that grassroots members are not necessarily encouraged to commit beyond the purchase of shares. And it leads to my fourth point regarding a kind of dilemma of scale, because on the one hand, local rootedness grants legitimacy to energy local communities and cooperatives, for sure, what we call resistance commons, identified by strong embeddedness in the local area and rules adapted to the local context, as well as indictment of leading companies, the fight of David against Goliath, as you can see in this extract of an interview. So taking part in a project in a local area can be, of course, a trigger for further participation for inhabitants. That's clear. But at the same time, local exclusiveness, which creates the confidence needed to act, can also limit the scope of the project, more broadly speaking, as a societal alternative. So there is a double relationship, in fact. of competition on the same scale between different energy cooperatives and of coordination between different levels. Some cooperatives have adopted rules of territorial self-limitation precisely in their statutes in order not to encroach on the development area of others. And at the same time, there are issues of practical coordination at different scales because of technical questions. Cooperatives organize at networks to be more effective regarding sharing expertise, lobbying, or to acquire professional skills, for instance. So you can see on this figure interaction between the key players involved in a very local energy cooperative in Saverne in Alsace, indeed. And as you can see, regarding project design, as well as funding, as well as concrete actions, there are a lot of stakeholders. And that's really, concretely speaking, the issue of networking and multi-scalar relations from Europe to very local issues and actors. And it's quite the same if we consider a joint Franco-German cooperative this time, Zusammen Solar Colmar. As you can see, same issues, multi-scalar dimension, a lot of stakeholders. So as a matter of conclusion, regarding energy cooperatives in the Upper Region, we can consider that collective action is fully embedded within the social world. One risk would be to bolster the position of an economic elite or to produce new exclusive circles of environmentalist actors claiming sole legitimacy to act to achieve energy transition. Even if it is defined as a common good, I mean the energy, the process of transition is embedded within what could be considered as club good strategies, I mean selective ones. And that's why there is a process of ever-changing transactions in terms of territories and actors at stake. These transactions over renewables in the Upper Rhine region embrace regulatory, economic, technical, as well as socio-political issues. Regulatory issues, making European and regional or local regulatory frameworks match each other, dealing with planning documents, feed-in tariffs, and so on. Economic issues, dealing with incentives, especially the cost of electricity, as well as issues of scale, because when we have different scales, then the profitability is not the same. And an important result considers the role of go-between actors dealing with expert supports for local governments as well as for networks of cooperatives, if they want to disseminate. Finally, there are properly socio-political issues, agreeing on the principles of the energy transition. Does it mean better or less use of resources? Enabling other actors to take part, not only the biggest ones. Using price as a lever to make renewable energies attractive. Local reappropriation of energy issues, what I told, not only end of the pipe. Relation between general interest and local interest, I mean the issue of solidarity between territories when we told about very local cooperatives, and encouraging individual action, of course, you and me, but at the same time recognizing the different capacities to act regarding social structure. For instance, if you are a landlord or a tenant, it's not the same regarding photovoltaics. So thanks a lot for your attention. And if you are interested, let me mention to be published soon a collective book precisely from the RESTIAMO project about cross-border renewable energy transitions. Thanks a lot.
Hi, Philippe. Thanks a lot for your very interesting presentation. It is also very interesting that the project covered this this aspect of okay, this is not, let's say, my field, but I would like to ask you a question regarding, technically speaking, how did you collected all this data?
Yes, in fact, we consider more or less qualitative data. I mean about 100 interviews with people, key actors, I mean, in the 3 national parts of the Upper region, as well from the French part in Alsace, then the German part in Baden-Württemberg, and the north of Switzerland. And what is important, I think, it is not only to consider key actors, that's one level, I would say, but as well as grassroots members of these cooperatives. And I think it's very important, sociologically speaking, to consider not only representatives, but also people who are grassroots members, because sometimes they are not the same representation about energy and energy issues.
Thanks a lot for the clarification. So let's go to the last speaker, that is Ulrich Filippi Oberegger from EURAC, and with the paper BUILTHUB, Dynamic Building Stock Knowledge Hub. Okay. You can share your screen.
Thank you. Can you see my screen?
Yes.
Okay. So hello to everybody, also from my side. I'm going to present you the Horizon 2020 project BUILTHUB. This project starts from the fact that not so much is known about the European building stock, which is easily and openly accessible. So BUILTHUB looks at how to develop a sustained data flow about European building stock to the observatory that exists for the European region. BUILTHUB will develop a roadmap for the Commission telling what should be done in order to have in the future a detailed view about the European building stock. It is creating a community, and we are also collecting data in a web-based data platform where we want to demonstrate services that will then be useful to stakeholders to have knowledge about what is happening in the European building stock, how the European building stock is transitioning towards a decarbonized, hopefully, building stock. I'm coordinating this project. It's a coordination and support action lasting for 4 years. We are now at the end of the first year. And the main roles of the project are to show how data can be collected, shared, and how added value can be created out of this data. We are building and engaging a community, showing best practices about data to knowledge processes, and we are developing data governance and services demonstrated through our platform. And finally, we are coordinating actions among other European and in general projects. In a visual representation, we see here what the project is all about. So we start from our web-based platform where data is now being collected and represented. We are now in an alpha stage for the first prototype. So the platform is tested internally first, and then it will be tested by pilot users and external stakeholders. And at the end, it will become public. We have different data sets, as I will show in a later slide. And we engage with the community to get feedback about this web-based platform and improve it such that the technical needs and requirements of the stakeholders are fulfilled. In the end, the overall goal that DG Energy pointed out and the European Commission, pointed out in several discussions is that the Building Stock Observatory, which is already public and accessible, will be kept and should be enriched, and the gaps in the observatory should be filled. We are also in contact with big data projects such Big Matrix Beyond that you see below. So we start from monitoring the building stock, and here you can see some thematic areas, goes from the general characteristics over envelope performance, technical building systems, energy consumption, energy performance certificates, economic parameters, to smart grid and e-mobility readiness. What we want to do is provide insight. We want, first of all, to render the data accessible and to allow download of this data, but also high quality metadata and general quality check of the data. to give analytics, visualizations, and also plans and scenarios for the evaluation of policies. We are mapping stakeholders and data sources and data providers. And in the end, we will propose solutions about how to create the most out of the data and how to make them fair, which means findable, accessible, interoperable, and reusable, to deal with the aspect of privacy and intellectual property and how data can be shared, of course, respecting these regulations, and in the end also how we can motivate data sharing. So there can be either a simple obligation or there can be incentives such that people are willing to share in exchange of services. As I said, we are building and engaging a community. So we did a mapping of stakeholders. We invited them to join our community. We did surveys and interviews, and you can see other actions which will follow, quite a lot of them. In the future, we have lead users, which are researchers, real estate developers, designers, and in the end, also national and local authorities that will be involved. I showed you some results. So we have now quite a few contact details and people willing to completely or partially share data with BUILTHUB. About 50 stakeholders said that they are interested in the data and willing to share their own data. The interest lies in research, as you can see, and analysis, in training and education, but also environmental decision-making, so policies for decarbonization and energy efficiency solutions. Here you can see that there is a wide range of different kinds of stakeholders, from academia to industry and designers and policymakers, energy agencies in all around Europe. Here, the ideal functions and benefits of such a data sharing hub are shown from the viewpoint of the stakeholders. So they are very much interested in having simply access to more data, but also to analysis and processing services, to networking with the community, and to infographics and visualizations. We also did some interviews with experts. We did about a bit more than 10 interviews, which are an analysis where we ask what they consider as benefit of such a platform, what kind of data analysis they think BUILTHUB and in the end the EU Building Stock Observatory should deliver, what kind of conditions are needed to allow data sharing, etc. What I'm doing and all the consortium is doing is quite some networking and outreach. We are in contact with the main actors such as Eurostat and with many other projects and actors dealing with data about the European building stock. Our web-based data platform looks like this. So we have it's quite a complex structure, but the central core is a graph database, which allows to put heterogeneous data sets together and query data among all these data sets. And there can be a manual access by a general user with visualizations, and as you would expect from such a platform, but also the programmatic access through an application programming interface for software developers, for example, to add services to the platform. We have collected quite a few data sets, and we will continue to do so throughout the course of the project. And these data sets range from building stock related to socioeconomic and climatic. Here you can see some examples. This slide shows the first prototype of the platform as it looks now. It's, as I said, an alpha version, so there's going to be changes. So stay tuned about that if you're interested. This shows for software developers, for example, that there will be the possibility to query more in detail and to have programmatic access to the platform. And here I wanted to show that we also want to estimate missing data. So a big problem is that quite a few data is missing, and it's difficult to get data about all the countries and all the years for the European building stock, and so we use machine learning techniques to fill these gaps. And this slide gives an example, but we explore all kinds of machine learning techniques like clustering, for example. Yeah, and with this, I'm coming to an end. So if you are interested in getting involved, you can get engaged with the project in many ways. We offer you access to the building data platform if you are willing to test it. You can then browse, of course, all the data we have and see if the services we provide, so for now, especially visualization and download, but then also scenarios and plans are to your liking and what you would improve. Of course, if you have data, we are always interested in giving you visibility and using your data to do further analysis, but you can also simply promote what we are doing so that you think that data sharing and collection of data in a responsible and reusable way is important. And you can, of course, also just interact with the other stakeholders. And in the end, simply follow us, of course. So feel free to contact us at the emails I put here. Yeah, I conclude here. So there will be a project video coming very soon. It's practically published in these days on YouTube, so you can check that out. And on the website, you can also find a brochure which gives some more information and re-summarizes what I told you today. This is the consortium consisting of 8 partners. And yeah, with this, I thank you for your attention and I'm available for any question. Thank you.
Thanks a lot for your interesting presentation. And I will see if there are some questions in the Q&A or in the chat. Okay. No question. I have just, because we have a couple of minutes. So my first question that probably you already replied, when the platform will be available to the end user? So for the...
Yeah, we are now in an alpha version.
Okay.
And we will do first an internal testing.
Okay.
Then we will move on with the pilot users, where external stakeholders are invited to test the platform. So this will be a beta version. And then when we think it's ready to share with the public, we will go public.
Okay, so
first, of course, we want to ensure that it works properly, and then we will allow for a discussion community where people can, of course, report bugs and give general feedback on what they would like to have implemented, what should be improved, etc.
Okay, thanks a lot. Then the second question that actually you had already a slide regarding this question. Which kind of, so the main input of your application, which are the main inputs of your application? Because I saw in the slide also other European projects, probably like Tabula. So you utilize it not only like simple data, but also the data from the other European projects.
Yeah, we are using about, at the moment, 45 data sets.
Okay.
And these are all quite big. So it's, for example, Eurostat is considered as, on the whole, as a source of data. Then we have different projects that collect the data. We have all kinds of databases, from climatic data to financial databases, economical databases. And we put all these together, and then we are asking how we can create added value by combining these data sets. So a simple example would be, if we know the floor areas of buildings and if we know the energy consumption, we can compute energy use intensity, just as a very simple example. Or if we know how energy performance certificates evolve through time, we can do an estimate how fast the EU building stock with the business as usual scenario will evolve. And then we can say, okay, what happens if we double the renovation rate? How much would that cost? How far can we go with the decarbonization? How much can we reduce CO2 emissions? So to answer these questions, what the Commission is very interested in, of course, and DG Energy, for example, is very interested in, is that you can create such scenarios. And I think also many stakeholders would be interested in that. You have a resource where you can refer to the European building stock, and you are quite sure that the data is correct.
Thanks a lot. Very interesting. So we are at the end of the session. So I would like to thank all the speakers. And okay, Sustainable Places will continue also tomorrow. So I hope you will enjoy the conference. Thanks again for your speech and interesting presentation.
Thank you.
Bye.
Thank you very much.
Thank you very much.
Bye.
Goodbye.
Bye.
Bye.
Thank you. Goodbye.
I will close the session.